Okay, so last time we were talking about chapter 12, which is bonding, and we talked about three different types of bonding, two main types, which is ionic bonding. And as we talked about, that is always between a metal and a non-metal. And remember, as we talked about, because of some of those periodic trends, metals have all those trends where they want to basically give away their electrons. And non-metals have pretty much all the trends of they want to hang on to their electrons and actually gain some more electrons. So when these two guys get together, we always get that transfer of electrons that go from our metal to our non-metal. As we talked about, the result of that is going to be some ions are formed, our cation from our metal and our anion from our non-metal. And remember that there is that electrostatic attraction. There is no sharing of electrons here. And we do get that full sort of transfer of electrons. And that's different than covalent bonding that we talked about. Covalent bonding is typically between two nonmetals. And because they both are pretty much on the same spot on the periodic table, they will share very similar periodic trends, which means they both really want to hang on to their electrons. They want to gain electrons. So what happens when two nonmetals get together is the best that they can sort of agree upon is sharing those electrons. So nobody's going to completely give away their electrons in this situation. They will share the electrons. And as we talked about, if we have equal sharing of electrons, that is what is sometimes referred to as a nonpolar bond or nonpolar covalent bond. And if we have unequal sharing of electrons, that is what is referred to as a polar covalent bond or just a polar bond. Remember, really the difference between these two sort of covalent bonds is they are both sharing electrons, but in a nonpolar bond, those electrons are being shared equally. So you can think of it as almost like a neutral bond. There's no side that's more positive or negative. Sort of like what we talked about with F2. These guys are going to share the electrons equally, so that's going to be a nonpolar bond. But when we swap out a hydrogen, fluorine for a hydrogen, we will get that difference in electronegativity, which is really the thing that determines how the electrons will be shared. And the fluorine is more electronegative, which means the electrons will really head towards the fluorine side that we can relate with a bond dipole arrow that we talked about. That again points to the side that's more negative in the bond. Part that's more positive is on that side. Thank you. And this is again, obviously a polar bond. We also talked about because of that unequal sharing of electron, what happens on the fluorine side is it creates a partially negative charge, which can be represented with that delta symbol, delta negative. And on the hydrogen side, it creates a partially positive charge. As we talked about, there's still partially positive and partially negative because there is still some aspect of sharing that's happening there. So unlike the ionic bond, their electrons have not been fully transferred. And as we, I think, finished up on last time or sort of where we left off, it is that electronegativity that is really the overwhelming thing that sort of determines how electrons are going to be shared. And a reminder that electronegativity is the ability of an atom to bring electrons towards itself. It increases as you go this way and decreases as you go that way on the periodic table, with fluorine being the most electronegative. So that's why in the case of like the hydrogen fluorine bond there, we definitely do see those electrons heading towards the fluorine side. I think we also talked about drawing Lewis dot symbols for ionic compounds. And remember that when you do that, you do have to include charges, right? Because electrons are being transferred from one side to the next. And ultimately, as we talked about, the goal of all bonding, be it ionic bonding or covalent bonding, is for everybody to achieve what is sometimes referred to as noble gas configurations. So they end up with the same electron configuration as the noble gases, which are very stable. And as we saw in ionic bonding, the way that they're able to achieve that is metals will lose electrons and go backwards on the periodic table to the noble gas that comes before it. and nonmetals will gain the electrons and go forward on the periodic table and have the same electron configuration. In the case of covalent bonding, they achieve that by sharing electrons. Any questions on any of that stuff there, which I think is what we talked about last time? All right. So I think we're right around here with electronegativity and this idea of using it to help us determine what type of bond that we'll come across. So as I might have mentioned last time, do you really need to use difference in electronegativity to figure out an ionic bond? And the answer really is no. As soon as you see a metal and a non-metal, it's ionic. You don't really need to really worry about anything other than that for most cases. So I would say for the most part, we would use sort of electronegativity here to help us determine whether or not we're dealing with a nonpolar bond or a polar bond, and how those electrons obviously are going to be shared in that particular case. So as we go across periodic table, once again, up and to the right, it increases, and down to the left, it decreases. A guy by the name of Linus Pauling came up with a method to basically figure out what type of bond you would have based on electronegativities. And he gave a value of electronegativity from 0 to 4. 4 is the most electronegative you could have, and 0, not so much. So 0 is pretty much no electronegativity. So what we could do is, if we're looking at two elements within a bond and we're not sure how the electrons are going to be shared, we could do what is sometimes referred to as taking the change in electronegativity or the difference in electronegativity values, and you basically just subtract the electronegativity values for each element. You do it so you get a positive number is basically how you do it. And you look at that number. And if that number is anywhere from like 0 to 0.4, it's usually considered a nonpolar bond, which means we would expect equal sharing of electrons to happen. Now, if you have anything above 0.4 to below 2, that is typically considered a polar bond, which means we would also still have sharing of electrons, but they will be unequal sharing of electrons in this particular case. And not in all cases, but generally speaking, if you're above 2, that usually means you're not going to have any sharing. You're going to get an ionic bond that's going to sort of happen. Once again, we probably don't need to use that because a metal, non-metal will tell you it's ionic, and that's probably the better way to do it. The reason I say that is there will be some examples. For example, you take a metal and a non-metal and you do the difference, it's actually less than 2, but it's still an ionic bond. So the best way to remember ionic, metal, non-metal, it's ionic. And I'd probably use this for more so covalent bonds. Now, as you can see, nonpolar equal sharing runs from 0 to 0.4. So there is a range of sharing that's happening there, right? So there's a little bit of sharing that's occurring on, but it's still considered equal sharing. We might have talked about it last time. If you find a situation where you really have a 0 in terms of the difference in electronegativity, that is sometimes referred to as a pure covalent bond, which is still a nonpolar bond, but that means you got like the perfect equal sharing of electrons. So in the case of something that we've seen before, like the fluorines or the hydrogens, that is the deal. So let's take a look. This is a table of electronegativity values. Obviously, you wouldn't need to memorize this, but it would be provided for you, these numbers, if you needed. You do need to know, obviously, the trends, which way increases and decreases as well. So if we use this, for example, to look at the 3 sort of examples we did previously, we had sodium chloride, right? We had HF, and we had F2. There's the 3, I think, that we looked at last time. So if we're going to use this, we would look up the value for sodium, which is 0.9. We look up the value there for chlorine, which is 3. And basically, we would just take the difference in electronegativity values of 3 minus 0.9, and I'm going to go with 2.1. So 2.1, again, is above 2, which means we would expect this to be ionic. And once again, we really don't need that because it's a metal and a non-metal. The reason I say that is, for example, if you take a look at, I don't know, we'll take a look at lithium and bromine, for example. Lithium is 1 and bromine is 2.8, which means if you subtract that, that's 1.8, which is obviously less than 2, but it's still an ionic bond. So definitely just follow the metal, non-metal rule in that case. Look at fluorine. Fluorine is 4. And fluorine is 4, which means if we take the difference in electronegativity, that is 4 minus 4, which is 0. That definitely is going to fall under nonpolar. That is basically a pure covalent bond in this particular case. If we take HF, H is 2.1, fluorine is 4. Difference in electronegativity in this case is going to be 4 minus 2.1, 1.9. 1.9 is at the top of that chart there. It is less than 2, so that is going to be a polar bond, which, as you can see, means it's almost to the point where those electrons are going to transfer, but they're still barely hanging on, as 2-ish is sort of our transferring point, and it has a difference of 1.9, which definitely means it's going to be polar. Any questions on that there? Yeah. Would you have a chart for that? Yeah, I would provide you the numbers because that's crazy to make you try to memorize those numbers. But you do need to know the general trend if the chart's not provided. And sometimes you can just use the general trend to make a pretty good estimate as well. Yeah. Other questions? All right, so why don't you try some here? Why don't we do a little the bond between potassium and bromine, the bond between carbon and hydrogen, the bond between carbon and oxygen, sulfur and oxygen, and why don't we do carbon and sulfur? All right, use the difference in electronegativity values here on this table and decide, is it polar, non-polar, or ionic in each of these cases? And if it is polar, which way should that dipole arrow be drawn? Yeah. Electronegativity, if you did it, would get you something like 2, which should tell us it's ionic. And once again, without that, we have a metal and a non-metal, so we should know, again, it's ionic in this case. If we go to carbon and hydrogen, carbon there is 2.5. Hydrogen is 2.1. So our difference in electronegativity in this case would be 2.5 minus 2.1, which gives us 0.4. And that would mean that this is a nonpolar bond in this case. It's really the reason why the number goes to 0.4 is because that's pretty much all your organic molecules are carbons and hydrogens, and carbons attached to carbons, and they're nonpolar. So that's why it really kind of goes there. Is that perfect equal sharing of electrons in this case? It's not, right? It's hedging a little bit towards the carbon, but not enough to be considered polar. So it's still considered equal in this case. We'll roll with our carbon and oxygen next. We got carbon at 2.5 and oxygen at 3.5, which means if we take the difference in electronegativity, we are going to end up with a 1, which means that this should be a polar bond as well. And it should be drawn, the arrow pointing towards the oxygen, as that is more electronegative. Yeah. Any questions on that one there? All right, so we'll look at sulfur and oxygen. Sulfur is 2.5, it looks like, and 3.5 for our oxygen. So this is, again, going to give us a difference in electronegativity, 3.5 minus 2.5, which is 1. And that would mean that this is polar as well, heading towards, once again, here, that arrow, the oxygen side, yeah, being more electronegative. Any questions on that one there? Now, if we look at carbon and sulfur, carbon is 2.5. Sulfur there is 2.5, which means the difference in electronegativity is going to be 0 in this case, right? That means that this is actually a nonpolar bond in this case. So this is a really good example that you definitely can have different elements that can still share electrons equally and create a nonpolar bond. The reason for this is actually the location of those two elements on the periodic table. If you look at it, if you look at the location there of where carbon and sulfur is, they are, as they like to say in the place, diagonal of each other. It's sometimes referred to as the diagonal rule. Carbon's further up, but sulfur is further to the right. So they cancel out their differences in terms of electronegativity, and they actually end up with the same value. There's a few other places where you see that, like nitrogen and chlorine as well. Diagonal of each other, not directly below, but kind of down and to the right is usually that relationship. So there are some places on the periodic table where you'll have this diagonal relationship where you could get two elements that actually share the same electronegativity, again, because one is further to the right and the other one's further up, and they sort of cancel out their differences. Any questions on that there? So that's something to watch out for. Now, what happens if you don't have these numbers, but all you have is the knowledge of electronegativity in terms of where it increases and decreases? You can, in a lot of cases, make a pretty good guess as to whether or not you'll have a polar or nonpolar bond when you're dealing with something that is covalent. For example, if we look at our carbon oxygen that we looked at, carbon and oxygen here, carbon oxygen are in the same row, and that means that oxygen is further to the right, which means it is more electronegative and should yield you a polar bond. So if you're comparing two elements that are in the same row of the periodic table, the guy further to the right is probably going to be more electronegative, and that probably will give you a difference that will yield you a polar bond. So without the numbers, if you're comparing those, you can do that. Also, if you look at the bond there between, get rid of some of this erasing here. If you look at the bond there between our, what do we do there? Sulfur and oxygen, that is right here. And they are in the same group on the periodic table. And in the same group, the element higher up should be more electronegative. And that also will yield you a polar bond in most cases. So if you're trying to determine a polar bond and you're comparing elements in the same row or the same group in a periodic table, you can make a pretty safe guess that they're going to be polar because there's definitely a difference in electronegativity as they're in the same group or same row. So a lot of times you can make a pretty good estimate or guess by just knowing the general sort of increase and decrease in terms of electronegativity. Any questions on that there? Yeah. Pure covalent bond means that you have an electronegativity difference of 0. So like actually we did right up here, the fluorine, right? That technically is a nonpolar bond, but it's sometimes referred to as a pure covalent bond, which means you have like perfect equal sharing of electrons. Actually, this would also be considered a pure covalent bond when you have kind of an electronegativity difference of 0. I would probably say nonpolar. Most people will call it nonpolar. Sometimes though books will refer to it as a pure covalent bond, which just means it's a nonpolar bond. It just means it's like perfect equal sharing of electrons. So they both basically mean nonpolar, but in the case of 0 difference, sometimes books will call it like a pure covalent bond. Yep. Other questions? I would, for this class, just roll with nonpolar, even if the difference is 0, which is the same thing. All right. So like I said before, you need to know how to use that numbers if they're given to you. And again, if you're not given it, it probably means that you could just use the general trend to sort of figure it out. So as we saw, there are atoms with really big differences in electronegativity will typically form ionic bonds. That again is why when we put something on the left-hand side of the periodic table, something on the right-hand side of the periodic table, there's a pretty big swing in terms of electronegativity. And that's why we usually get those electrons being transferred, as opposed to when we start bundling everybody together there up in the non-metal region. Everybody has very similar in terms of electronegativity. You're not going to get a very big difference, and we're going to get some type of sharing that's going to occur there. All right, so as we talked about, metal, non-metal, ionic, and two non-metals being covalent bonding. So this again, as I talked about, just be careful with the ionic bond. It's better to just go with the metal nonmetals ionic rather than strictly going by electronegativity values, because again, there will be some that drop below that to cut off. Percent ionic character is something that is used as well to describe bonding. Not very much, but books like to throw it in there somewhere. But we don't usually use it too much these days. So instead of describing as sort of polar, nonpolar, or ionic, we just describe everything as ionic. So an ionic bond would be 100% ionic character because it's an ionic bond, and obviously 0% this way, and then obviously somewhere in the middle as well. So I would say percent ionic character is not used too much in terms of describing. More so it is either an ionic bond, polar, or non-polar bond is typically what we use. All right, so now that we talked about earlier drawing Lewis structures for ionic bonding, we're now going to talk about how to draw Lewis structures for covalent bonding, where we do have sharing of electrons. If you would like to get the correct structures, I suggest you follow these steps that we're going to talk about so that you actually do get the right structures. Sometimes people like to do it what I sometimes call piecework, where they just draw the Lewis dot symbols for everybody and try to figure out where all the electrons go and how they all sort of match up together. And usually what happens when people try to do that is they usually end up with the wrong number of electrons, not the right number of bonds and stuff like that. So it's better when we think about drawing Lewis symbols or Lewis structures for covalent compounds to think about the electrons as not really belonging to anybody. And that's usually what people try to do. They go like, well, nitrogen's coming in with 5 and oxygen's coming in with 6, and they has to do this or that. But just to properly distribute those electrons. So the first thing that we want to do always is to think about how all the atoms and elements are arranged together. That's sometimes referred to as the skeletal structure. There are some rules to help you decide, what should go where. In general, the least electronegative element is usually in the center. And in a lot of cases, everybody else is attached directly to it. You could have more than one central atom, but a lot of stuff that we draw will be kind of like one guy in the center and sort of everything attached, but not in all cases, though. We should never have hydrogen or fluorine in the center. That is because fluorine is the most electronegative, so it should never be there. And we already know we should never put hydrogen in the center because hydrogen will end up with what? Too many electrons, right? Because hydrogen should only have 2 electrons. So if you throw it in the center, it's going to have way too many electrons. So always on the outside. Once you sort of figure out how to arrange everything, probably the most important thing is this guy right here, is to count the total number of valence electrons that you have. That's in the entire sort of molecule that you're drawing. That number is really important because you need to hit that number right on the nose when you draw your picture. You can't have any more or any less electrons. It's got to hit that number. Now, you may be asked to draw what are referred to as polyatomic ions. These are things that are covalently bonded together, but actually have an overall charge. So if you're drawing something with a charge, you do need to adjust your number of electrons so that you end up with the correct number on your picture. So as we've talked about, if something has a negative charge, that means that it has gained electrons. So you need to add that number to your total. Otherwise, again, you'll be short electrons. And if something has a positive charge, that means it has lost electrons. And that should be positive, obviously. We do subtract that number from your total. So again, you'll have too many electrons if you don't subtract it. So that's really, really important. That's like the number that you gotta get everybody to. Once you got sort of the arrangement and you got the total number of electrons that you should have, the next thing that you want to do is draw one single bond from the center atom to each of the outside atoms. I personally use lines when I draw these things, but if you still want to use dots, you can, but lines might be good in this situation. Remember that when we draw a line, it represents 2 electrons. So you want to count up how many electrons you've used. You will have some electrons left over, which means all the remaining electrons that you have left over will go on the outside atoms in pairs of electrons, which are represented as dots. And you'll fill up all the outside atoms till they hit the magical number of 8, right? The octet rule. So you'll fill up everybody on the outside until they hit 8, except if it's hydrogen, because it should be filled with 2 already. If you still have electrons left after you filled up everybody on the outside, then you go to the center atom and put them on as dots as well, pairs of dots on the center atom. At that point, if you didn't screw up, you should be out of electrons at that point, hopefully. So now you basically put onto your picture all the electrons that you have available to you. The last thing that you want to do is make sure everybody meets the octet rule. And if they do not, that is the case where you should then think about making a double bond. And if that doesn't fix it, make a triple bond. So I think we talked about it earlier as well. You don't want a double bond or triple bond right out of the box. You kind of want to save it to fix something that maybe has not met the octet rule along the way. Questions on that there? All right, so let's do one together to see how we kind of go through all these steps. So let's take a look at this one here, which is NF3. So really the first thing I'm going to do is figure out the number of valence electrons. And remember that the number of valence electrons equals the group number. So nitrogen is group number 5. There are 3 fluorines, and each fluorine is group number 7. So that's going to be 26 valence electrons. So that is the magical number of what I need to hit when it's all said and done in this case. All right, so clearly I got nitrogen and fluorine. And frankly, fluorine is more electronegative than nitrogen, which means nitrogen should be in the center. I would say probably in our case, 9 times out of 10, you're going to have one guy in the center, and then everybody else is just going to be attached to it. So that's usually the general arrangement. So we'll go one in the middle. We'll throw some fluorines on the outside. To answer the question, no, it doesn't matter if I put the fluorine on the bottom or top. It doesn't really matter where you put it, but I'm just going to put it on the bottom here. All right, so the first thing I'm going to do is go from the center atom to the outside atom. I'm just going to draw one single bond, not double bonds, not triple bonds, just one single bond. At this point, I got 2, 4, 6 electrons, as each line represents 2 electrons. So if I just do a little subtraction, I got 20 electrons still to go. So those 20 electrons are going to go on the outside atoms in pairs of electrons. So this is going to be 2, 4, 6, and that one is full because it has 8. 8, 10, 12, 14, 16, and 18. At this point, everybody on the outside is filled as they all have 8. I still have, if I counted right, 2 more electrons to go. And at this point, where those electrons are going to go is to the center atom. They will also go on as pairs of dots, or 2 dots, basically, right there. That means I have now placed all 26 electrons at this point. Any questions so far? Last thing we want to do is just make sure everybody's met the octet rule. And we're just counting electrons. Doesn't matter if they're lines, dots, whatever it may be. So that is 2, 4, 6, 8 for that fluorine. 2, 4, 6, 8 for that fluorine. 2, 4, 6, 8 for that fluorine. And now if we go to our nitrogen, 2, 4, 6, and 8. So it also has 8. Everybody has met the octet rule, and this would be the correct Lewis structure here for NF3. Any questions on that there? So again, we want to think of these electrons as not really belonging to anybody. That's where people kind of go wrong, and they end up with the wrong number of electrons. You just want to evenly kind of distribute it to everybody that's in this particular structure. Any questions on that? All right. Let's see here. That's what I think you got next. So why don't you draw that one? Once again, I'm going to start with really the number of valence electrons. So we got 5 for our nitrogen. We have 3 oxygens, each are 6. And once again, this does have a -1 charge, which means it has gained electrons, right? So we do need to add that extra electron in for the charge. Otherwise, again, you're going to be off in terms of your number of electrons. It can happen in real life that you have an odd number of electrons, but in this class, it should not happen. Yeah, so everything should kind of come out equal or even in that sense. So we will end up here. That's a lot of math there. It's 1924 we'll go with here. So in this case, we have a nitrogen and oxygen. If you look at nitrogen and oxygen on the periodic table, looks something like this, which means oxygen is further to the right. They're in the same row. That means oxygen should be more electronegative. And I would say probably 9 times out of 10, if you have one element and 3 of something else, the one guy is in the middle and everybody else is attached to it, is pretty much how it looks. So we're going to go nitrogen in the middle there. We're going to do a little attachment here, some oxygens. So once again, we're going to start with just a single bond to each of these. So 1, 2, and 3. Once again, that is 6 electrons, which means I got something like maybe 18 more to go. Those are going to go on the outside as pairs. So 2, 4, 6, 8, 10, 12, 14, 16, and 18. That means at this point, I have distributed all 24 of my electrons. Is everybody good in terms of the octet rule? No, the oxygens are good. Each oxygen has 8, but the nitrogen has only 6 in this case, right? So if we kind of look at it here, each of these oxygens are exactly the same. So 2, 4, 6, but nitrogen has 2, 4, and 6 only. So it is short. So that's not good. So we do need to fix it. So at this point, we could try a couple of things here to maybe fix it. Can I just lay some dots there? I cannot, because now it has how many total electrons? 26, which is too many. So you cannot just add electrons to try to fix it. So in this particular case, we need to go to the situation of we need to make a double bond to see if we could fix it. Now, when we look at all these oxygens, are these oxygens basically the same or different things? They basically are same. So you can actually make a double bond at any of the oxygens that you want. So if I'm going to make a double bond in this case, can I just draw me a line right there? I cannot for the same couple of reasons. I now have 26 electrons, right, which is too many. And that oxygen up on top now has 2, 4, 6, 8, 10 electrons, which is too many for it as well. So we cannot just draw a double bond to fix it, but we do need to draw a double bond to really fix it. So when we make a double bond, what we're actually going to be doing is taking a pair of electrons, for example, from the oxygen, and we're actually going to be bringing them in to make that double bond. And when we do that, we will end up with something that looks like this. And put a little bracket around it, as you typically do with things that have charges. And now when we look at it, everybody should be good. And we still have only 24 electrons. So if we count up our oxygen here, 2, 4, 6, 8, oxygen to the left, 2, 4, 6, 8, oxygen to the right, 2, 4, 6, 8, and our nitrogen also now good by double bonding there, 2, 4, 6, and 8. So everybody has 8 electrons. There's still just a total of 24 electrons, which is exactly what we need. Question on that there. Yeah. It's equal to the group number. So remember, number of electrons equals the group number. So that's where the 5 comes for nitrogen, and right next door is 6 for group number 6 for the oxygen. That's where those come. Yep. We multiply it by 3 because there's 3 oxygens in this guy. Yeah. Yep. And then the +1 comes from the -1 charge on it. Yep. Other questions? Now, could we have double bonded to the left? We could have. So we could have done the double bond over here to the left, and you would have ended up with something that looks like this. Then obviously we have our guy there in the middle that we drew. As I Did not leave a lot of room there. So get rid of my bad arrow there. And we could also have double bonded to the right if we chose to do that. Look something like this. Now, all three of these structures, which have these double-headed arrows kind of between them, these are all related to each other. These are what are known as resonance structures. And what is a resonance structure? A resonance structure is pretty much what we just ran into. I could make the double bond up on top. I could also make the double bond to the left, double bond to the right. Those electrons that we brought in to make the double bond are sometimes referred to as being delocalized, which means at some time they may be over here, and they may be over here, they may be over here, they may be over here. So because those electrons are kind of moving around, we could draw three different structures in this case. They're all where sometimes referred to again as resonance structures. They're equivalent to each other. The real structures somewhere between all three of those molecules is really where that is. But because those electrons can move around, you could draw an equivalent structure, which is known as a resonance structure. The simplest way to remember how to do it is just any possible place you can lay that double bond, just draw another structure where you move the double bond. Any questions on that there? If you were asked to do this question, draw a Lewis structure, any one of the three would be sufficiently fine. If you were asked to draw all the resonance structures, then you should draw all three of the structures. Yeah. Any questions on that? All right. So let's do a few more just to make sure. Let's go Lewis structure crazy here, shall we? Draw SH2, SO2, NH4 plus, CO2, N2. While you're at it, why don't you draw nitric acid? By the way, nitric acid looks something like this. All right. Take a few moments there, draw up these structures. Let's take a look to see how you're doing on some of these. We'll start at the top here. Why not? We'll start with SH2. So we're going to calculate the valence electrons. Sulfur is group number 6, and there's 2 hydrogens, which each have 1. So that is 8 valence electrons. Clearly, in this case, as we talked about, we can't put hydrogen in the middle, so sulfur has got to go in the middle. So we're going to do our sulfur in the middle. We're going to do hydrogens. I'm going to do it on either side. It really doesn't matter, sort of, but I'm just going to kind of draw it straight across. We're going to do one single bond, badly drawn, to each of the hydrogens there. That is 2 4 electrons, which means I have 4 electrons to go. Should I put some dots on the hydrogen? Very good. We don't want an X, right? So basically the hydrogens on the outside there are done. Pretty much that's what they always should look like. As we talked about before, no double bonding hydrogen, triple bonding hydrogen, no dots around hydrogen or anything like that unless you like X's. Yeah, so don't do any of those things. So clearly our remaining 4 electrons need to go onto the center atom. Once again, they do come on as dots. And at that point, we have now placed all 8 of our electrons. And if we count up our hydrogens, obviously they have 2 on each side. The sulfur has 2, 4, 6, and 8 electrons, so it is good as well. Any questions on that one? Okay, so let's take a look at the next one. We're going to do a little SO2 action next. So SO2, again, valence electrons. We got 6 for the sulfur. We have 2 times 6 for the oxygen, 18 valence electrons in this particular case. Once again, if we look at where sulfur and oxygen are on the periodic table, once again, that general trend in electronegativity could help us here. We see that oxygen is further up in the group, right? They're in the same group. That means oxygen is more electronegative than sulfur. And once again, just common logic here, 1 sulfur, 2 oxygens, 1 guy in the middle, usually in most cases. So we're going to do our sulfur in the middle, oxygen's on the outside. Once again, we're going to do a single bond to each of them, and that is 4 electrons. In this case, we have 14 more electrons to go, so we are going to put them on the outside first. So 2, 4, 6. That then fills up that guy on the right. 8, 10, 12. That now fills up that guy on the left. We have now put a total of 16 electrons, right? I still got 2 more to go. They should end up where? Should end up on the sulfur as dots. And that's how the dots get there, and they should be there. So that, again, is where you want to do. You want to make sure you place all your electrons first before you even think about double bonding or triple bonding. Otherwise, you will end up with the wrong structure. People like to double bond both sides on this. Incorrect in this case, yeah. Speaking of that, is everybody good? Everybody's good except the sulfur, right? The sulfur in the middle only has 6 electrons, right? So it's got 2 there, 2, and 2. So here we can make a double bond on either oxygen. So remember that when we make the double bond, we're actually going to take a pair of electrons and bring them in to make that double bond. So I'm going to do that, and that will give me a double bond to the right here. We will still have the single bond over here. And now everybody has 8 electrons. We still only have 18 electrons in this case. Question on that there. Could I have double bonded on the left? So this is another one where you can draw a resonance structure, right? And if you drew the resonance structure, it would just be double bonded on the left in this case, single bonded on the right, and those would be 2 resonance structures of each other. Again, if you're just asked to draw the Lewis structure, either one's good to lay up in this case. Question on that. Can't tell you how many people, like I said before, would double bond both sides and no dots. So it's really important. Distribute those dots first before you even think about double bonding or triple bonding. Any questions on that one there? All right. We'll go to NH4 plus next. So nitrogen is group 5, so it's got 5. There are 4 hydrogens each at 1. With the plus charge, I should add or subtract? Subtract, right? Because I lost 1. So that is why we are subtracting. That's going to give us 8 valence electrons in this case. And that means nitrogen definitely has to be in the middle here, as hydrogen cannot. And we're going to do a single bond from the nitrogen to each of the outside ones. And that is 2, 4, 6, 8. That looks like a winner in this case, yeah. Nitrogen obviously has 8. Each of the hydrogens have 2. Good to go. Again, a bracket and the charge on the outside on that one. Any questions on that one there? All right, continuing on here. CO2. We got 4 for the carbon, 2 times 6 for the oxygen. 16 we'll go with here. Once again here, carbon and oxygen are in the same row on the periodic table. Oxygen is further to the right, which means it's more electronegative, and there's only 1 carbon, so that seems like it should go in the center there. All right, so same deal, single bond. That is 4 electrons, which means we have 12 more to go. So 2, 4, 6, that's going to fill up the outside there. 8, 10, 12. Now, in this case, is everybody good? Carbon is short, right? Carbon has only 4 electrons. So it's got only 2 and 4 electrons. So we can make a double bond to try to fix it. So we're going to take some electrons and bring it in to do so. And if I do that, that's going to give me a double bonded oxygen on the left. Did that fix it? It did not. It got better, right? Now carbon has got 6. So this case is also something you want to think about. You may be tempted to jump out to a triple bond at this case, which you technically could do. But we still have an option to make another double bond on the oxygen, right? And that is probably the better move. So what you want to do is kind of use up all your options for double bonds. And then if there is no more options, then go to triple bond. That's usually will give you a pretty good structure. So in this case, we're going to actually bring electrons in on the other side. And we're going to double bond it up over there. And that's going to give us a double bonded oxygen on the left. a little double bonded oxygen on the right. And in this case, now everybody has 8 electrons, including the oxygens. And we still have only 16 electrons in this particular case. Any questions on that one there? All right, we'll do one more here and we'll stop. We'll look at nitrogen and we'll go over the last two next time. But we'll take a look at nitrogen here, and that is N2. And that means I got 2 times 5, which is 10 valence electrons, right? In this particular case, there is no center atom, right? It's just 2 atoms, right? So there is nobody in the center. So you could just put them side by side. And you really could just do the same steps that we did before, which is connect them together with a single bond. So that is 2 electrons. We still have 8 more to go. We'll put them on the outside. So 2, 4, 6, 8. That is all 10 electrons. Are both nitrogens good? Yeah, the one on the left is a little short, right? It has only 4 electrons. So we just go through our process, which means now we want to make a double bond. So just like we did before, we're going to take some electrons and bring it in to make a double bond. And we will end up with a double bond that looks something like this. Is the nitrogen on the left good now? It is not. It has only 6. So at this point, there is no other way or place to make a double bond. So now we could progress to a triple bond. Triple bond works the exact same way as a double bond, which means you need to take a pair of electrons and bring them in to make that triple bond. And we will end up now with a triple bond here. Now are both nitrogens good? They are, and they have only a total of 10 electrons. So again, that is how nitrogen gets to a triple bond. Got to keep making it. So it's really important to keep that in mind. Like I said, 2 very common mistakes people make. They just want to like double bond and triple bond right out of the box, and they want to throw a bunch of stuff on hydrogen. So don't do either of those things. Any questions?